12-factor is a popular methodology for building software as a service web apps. It's a set of best practices designed to enable applications to be built with portability and resilience when deployed on the web. Large platforms like AWS, Google Cloud, Azure, Heroku, and even service platforms like GitHub and GitLab and Bitbucket have all evolved their service offerings with the 12-factor methodology in mind. So the more you understand it, the better. But 12-factor methodology was created with entire web platforms in mind. So what about your serverless projects? Suppose you wanted to implement 12-factor methodology for a microservice that you deployed to AWS Lambda. Can you do 12-factor for that as well? And what would that even look like? Well, the short answer is yes, you absolutely can, but you should consider a few things. Let's get into it. We're going to be looking at a live, actively maintained project today, which I use as a teaching tool for cloud architecture, DevOps, and AI courses at University of British Columbia. It went into production in mid-2023, and it's a complete full-stack project written in Python, React.js, and Terraform. But for purposes of this video, we're only going to look at a single AWS Lambda function, focusing on how all 12 factors have been implemented. By the way, you'll find links in the description down below for any URLs that you see over the duration of this video. Also, you can fork or clone this repo and you can build the entire solution yourself in just a few minutes, and I hope that you give it a try. And if you do, then don't forget to give it a star. Also, I use this repo for multiple videos, so if you see anything else in here that you want to know more about, then leave me a comment down below and I'll definitely take your suggestion into consideration. Let's start with 12-factor methodology. What exactly are the 12 factors? And what's involved in implementing each of these for AWS Lambda? The good news is that with an AWS serverless implementation, a lot of these are taken care of for you. And so conversely, this video will focus on how to address everything else. Okay, let's work backwards. Our subject Lambda is named Lambda OpenAI v2, and it backs a REST API endpoint that's in production right now. It allows you to interact with the OpenAI Chat Completion API. So what it does is pretty easy to understand, and more importantly, it's implemented using 12-factor methodology. This is Postman. It's a user-friendly desktop application for interacting with REST APIs. Basically, it just creates curl commands and runs them in the background, but it also gives you prettified results. And here's the Lambda itself, deployed to AWS as viewed from the AWS console. There actually are 3 Lambdas in this project, and each of these is using a common distribution package of the source code, with the only differentiator being the value of the AWS Lambda handler. What you see here is highly influenced by factor 5, build, release, run, and factor 10, dev, prod, parody. And I'll apologize to you right now for needing to skip around, but unfortunately it's unavoidable. Anyway, factor 10 is the driving reason that each Lambda is using an identical code package. Since the project includes unit tests that run in multiple environments, and because the project deployment is automated with Terraform in order to satisfy factor 9, disposability. Anyway, standardizing the code package simplifies things a great deal. You can also see a couple of non-Python assets present in the file system. These directly bear on factor 3, config, which we'll get into in just a moment. But let's pause for just a second and zoom in on this handler value, because I regularly run across blog posts and Stack Overflow responses that kind of misrepresent how this actually works. And the good news is that it's a lot simpler than some of these online posts would have you believe. Essentially, your handler is exactly the dot-notated path that the Python interpreter needs in order to locate the Python function depth that it's supposed to execute when the Lambda itself is invoked. If you're following best practice in your Python source code, then you're also using this exact same path for any local imports in your source code. Okay, back on point. There are a few things besides the source code package itself that this, and most Lambdas in general, need in order for it to actually work. First, we need to set some environment variables, which in this case are the OpenAI API credentials, as well as a couple of production-specific settings. And second, we need to ensure that this Lambda has been granted the permissions that it needs in order to be able to interact with any other AWS services that are referenced in the source code. Okay, let's quickly run through these 12 factors. Okay, number 1, code base. One code base tracked in revision control with many deploys. This is easy. This idea is deeply embedded in Git itself with branch and merge paradigms. But it's further reinforced with features that have evolved over time in platforms like GitHub and GitLab. In GitHub, for example, tagging, package releases, and GitHub Actions, all of which are in use in this project, are good examples. And to an equal extent, platforms like Heroku and the big cloud infrastructure platforms all provide tools that kind of assume that you're using a single code repository, as this bears on their service offerings. Number 2, dependencies. Explicitly declare and isolate dependencies. This would be easy thanks to pip, except that we're also using AWS Lambda layers for this project, and there are a lot of moving parts to this in order to satisfy factor 5, build, release, run, and factor 9, disposability. I made this video about how to create AWS Lambda layers with Terraform, and you might want to check that out. More generally though, languages like Python, Node, and Rust strongly reinforce this idea with some explicit declarative way to describe usage of third-party code. On a positive note, using AWS Lambda layers gives us some additional separation between the Python dependencies and our own code with regard to when, why, and how frequently each needs to be updated. Number 3, config. Store config in the environment. Now, this is by far the hardest factor to implement well. And also keep in mind that factor 5, build, release, run, and factor 6, processes, and factor 10, dev, prod, parody, all depend on how well this factor is implemented. And in turn, this factor depends on how well factor 6, processes, is implemented. That is, the extent to which your code is stateless. In this project, literally a full 1/2 of the source code dwells on configuration. Here's a simple example of what you're striving to be able to do with a good configuration strategy. Similar, say, to Django, you have an importable module that contains your configuration data. Your code shouldn't need to dwell on how the configuration data inside this module came to exist. It should just assume that it's there and that it can get whatever it needs from this single source. Your code shouldn't need to validate anything, nor do any data type conversions. It shouldn't need any awareness of where it's running or what environment it's in. If, for example, you're supposed to be using one set of OpenAI API credentials in dev and a different set in prod, then this additional complexity should be handled entirely by the config rather than by your code. So to ensure that that's crystal clear, here's what I mean. If you import both the settings as well as the settings class from which it was instantiated, then you should be able to exactly duplicate the settings data with a single line of code just like this. In fact, the only benefit you're actually getting from the settings import is a bit of a performance boost during cold starts. This project implements a singleton class for settings, and that's generally a pretty good optimization. But you could skip this if you wanted and just initialize settings directly from the settings class, and it probably wouldn't affect your performance that much. Okay, let's focus on AWS region for a minute, since you definitely need this in your project. And I'll use this to illustrate how config gets really complicated really fast. I'm going to instantiate a settings object, but this time I'll actually pass a literal hard-coded value to the constructor. And so in theory, what I pass to the constructor should be what I get out of the object afterwards. Now, I know it seems stupidly obvious, but just bear with me for a second. Sidebar comment about this settings class. I implemented it with Pydantic, which I'd highly advise you consider doing as well in your project. Basically, this will give you the ability to create a class whose properties behave similarly to the fields in a relational database, in that they'll be strongly typed. Plus, Pydantic can handle pretty sophisticated scenarios for managing default values as well as validation logic. We could, for example, set up a regex expression and validate incoming AWS region values against that, but we can do better. Instead, we'll grab a list of valid region codes from the AWS CLI at runtime, but more on that in just a second. For now, let's focus on how default values are handled, because this really is where the complexity is introduced. First up, Pydantic gives you an out-of-the-box ability to initialize a field with a bash environment variable if such variable exists. So that's amazing. In dev, CI/CD runners, test, prod, you name it, All you have to do is ensure that the right environment variable gets set up with the right values, and then Pydantic takes care of the rest. Cool. But as a fallback, you can also pass it a default value, even as a Python variable if you prefer. And you can get as sophisticated as you want with this. In this case, you can see that the default value is delivered from one of two sources, depending on whether this tfvars returns anything. tfvars, by the way, is a Terraform thing. Remember that factor 9, disposability, requires that we take an infrastructure as code approach, which in this case is Terraform. And so, if our Terraform configuration specifies an AWS region, and it does, then this is what we should be using unless something different came in via the constructor. So here's what all this looks like in practice. If we receive a value from the constructor, as we do in arrow number 1, then we should use this. Otherwise, we'll read the value of this environment variable, that's number 2, if it exists. Otherwise, we'll set the default value, number 3, which itself depends on whether our project uses the Terraform tfvars file and whether it includes a value for AWS region, which is arrow number 4. But there's some curveballs as well. This settings module leverages python.env to look for and load a .env file if it can find one. That, incidentally, is an alternative vehicle for initializing environment variables for Pydantic. But it's also a way to introduce custom environment-specific initialization behavior, which we definitely need in the case of this project because, for example, in prod, the AWS region isn't really up for discussion. Instead, we need to figure out from within the prod environment itself in which region we find ourselves. And secondly, we're using IAM role-based security, and so ultimately, anything having to do with regions is going to be subject to the policies we've applied to the role that we've associated with this Lambda. Okay, let's summarize all that. Any custom logic that we've added inside the constructor trumps everything. Otherwise, we use the value passed to the constructor if it was passed. Otherwise, we use the value from the .env file if it exists, if it contains a key value pair for AWS region. Otherwise, we use an environment variable if it was set. Otherwise, we use whatever we'd originally set in terraform.tfvars if it exists and if it contains an AWS region. And finally, we have a hard-coded system default value of US East 1. And that, my friend, is why config is hard. A couple more things. I mentioned validating the AWS region value against a list from AWS CLI. Here's how you can do that. Bullet number 1 is a simple list comprehension that you can generate using the EC2 endpoint of the AWS CLI via Python's Boto3 library. This is a module level declaration, so it only runs at startup and it's generally pretty performant. The fancy part is bullet number 2, where we're using Pydantic's new @field validator decorator along with a cool coding trick to read those region codes from a Pydantic property named AWS regions. Also note that there's a snippet here on line 628 that deals with null values and empty strings, just to ensure that these are correctly dealt with. Okay, last thing. Pydantic gives you a way to make your settings immutable using this really simple subclass pattern, and so that's pretty nice. Let me show you what I mean. If you go to a Python prompt and you import settings, then Pydantic should raise a validation exception if you attempt to modify the value of any property because the instance has been frozen. All right, that's config. The rest is pretty simple by comparison. Let's keep going. Number 4, backing services. Treat backing services as attached resources. This is easy, and it's so strongly reinforced by the simple existence of cloud infrastructure providers that it's practically become second nature. We're not only talking about persistent strategies like databases and file systems, but really cloud service provisioning in general. Number 5, build, release, run. Strictly separate build and run stages. This is modestly challenging because the concept of strict separation surfaces across multiple technologies in your project. And also, of course, because you have to do the work, and it's a lot of work. You should check out my other videos on setting up advanced CI/CD features in GitHub. Modern frameworks like Django and React.js include build tools. And CI/CD platforms are purpose innovated to provide you with the kind of unique feature set that's required to remotely build, package, distribute, and deploy your solution. This project makes use of both, but it also implements additional automation via a makefile. And release is implemented as a GitHub action, while deployment is independently managed by AWS API Gateway and initiated with Terraform. So you can see that overall we're using several different kinds of tools, each playing some kind of a role within a 12-factor paradigm. Number 6, processes. Execute the app as one or more stateless processes. This really is only hard because making your code stateless is wholly dependent on factor 3 config and factor 4 backing services. And we've already covered both of those. Besides, serverless infrastructure like what we're using for this project is inherently stateless. Neither API Gateway nor Lambda provide storage solutions, for example. Number 7, port binding. Export services via port binding. This is easy peasy. This is a really simple solution implemented as a REST API that's available on ports 80 and 443. And so once again, the infrastructure that AWS offers is inherently compliant with 12-factor methodology. Number 8, concurrency. Scale out via the process model. Most of the value proposition of stateless services like AWS Lambda have to do with their ability to manage concurrency really well. Well, it's that plus your diligence in implementing stateless code with clean objects. This is naturally related to number 6, processes, and speaks to the stateless nature of how our code runs, with the goal being that we can deploy as many autonomous instances of our code as we need in order to meet demand. We achieve this for free since we're using AWS serverless infrastructure, which is inherently and infinitely scalable. While writing your code, you do need to try to visualize how this is working in practice in order to ensure that you're not doing anything in your code that might undermine its statelessness. Number 9, disposability. Maximize robustness with fast startup and graceful shutdown. This is easy to think about, but I'll tell you, it's really hard to do well in practice. This is the second hardest factor to implement, behind factor 3 config, namely because writing Terraform code like what you see in this project, it's knowledge intensive, it's a little bit hacky, and it's pretty hard work in general. Also, be mindful that in an abstract sense, you can apply the spirit of the idea of this factor to your Lambda source code package as well. Fast startups only happen with modular, compact code packages. So if your bundle becomes bloated, where you're dealing with gigabytes of dependency data inside the Lambda itself, then this will undermine even the best laid infrastructure plans. Number 10, dev prod parity. Keep development, staging, and production as similar as possible. This is challenging, but only in a general sense. There's nothing specific to Lambda itself, mind you. Now, the first time I ever set out to do this with Lambda, it took me a while to get my Python code organized so that it could thread the needle, so to speak, of all the, I'm speaking about the requirements for the various environments in which it needed to run, and then also to get it built and packaged and distributed the right way and automatically. The devil is always in the details with this kind of stuff. The closer you ultimately get to achieving parity between dev and prod, the simpler your build deploy logic will be. And that's the whole point. Number 11, logs. Treat logs as event streams. AWS CloudWatch takes care of most of this for us. Of course, you do need to create meaningful log entries and in the right places and at the right times. This code does all of that particularly well, but that shouldn't overshadow just how awesome AWS CloudWatch is. It's a real luxury to have a unified logging platform. One side comment about logging that's specific to AWS serverless projects, especially Lambda and API Gateway. With both of these, you have to get the CloudWatch logs working early on in your project, because without these, you'll have no means of diagnosing runtime errors in both services. And this will drive you absolutely mad. Without you being able to generate log data to CloudWatch, your Lambda simply won't work, and you'll have absolutely no idea why. Last one, number 12, admin processes. Run admin management tasks as one-off processes. This is kind of a no-brainer. The three primary tools at your disposal for a project of this nature, Terraform, AWS CLI, and the AWS console, are by definition admin tools. So you kind of got this one entirely for free. And that's it. I hope you found that helpful. And if you did, please consider liking and subscribing because that really helps. But either way, I will see you in the next video.